Okay, we're going to talk about two concepts, basis and dimension. These two concepts are very closely related. Basis, you can think of basis is a primitive set of vectors that span a subspace. For instance, if you're in a plane, for instance, if I'm in the plane of this page, I could actually take any two linearly independent vectors and that would form a basis of this plane because the plane is the span of these two vectors. And furthermore, if I take any one of these vectors away, it no longer spans the plane. So I could say the basis is a minimal spanning set. Basis is a minimal spanning set. Dimension, on the other hand, can be identified as the number of vectors in the basis. Okay, and this is in accordance with our intuitive notion of dimension, that this plane here has two dimensions, and that's the number of vectors in this minimal spanning set. So we'll get into these ideas a little more in subsequent slides. Basis. All right, a basis for a vector space is a sequence of vectors that is linearly independent and spans the space. So again, we see the notion of span is key for basis. We also have this linearly independence. Right, because a basis is a sequence, meaning that bases are different if they contain the same elements but in different orders, we denote it with angle brackets. All right, so this notation indicates the basis. The first element of the basis is B1, second element is B2, and so on. All these B's are vectors in the vector space. Okay. So here's a basis for R2, 1, minus 1, and 1, 1. If I plot these two vectors, 1, minus 1, 1, minus 1 looks like it's this way, and 1, 1 looks like it's this way. So we can definitely see these two vectors are linearly independent. They're not multiples of each other. And you can also see that they span the whole plane. You can see that geometrically because any point here, for instance, could be expressed as a multiple of this vector plus a multiple of the other vector. And that's true no matter what point I choose. That can be expressed as a multiple of this vector here, and so on. Okay, so if we prove this algebraically, this set of vectors is linearly independent. We can prove that by trying to form a linear relation among the vectors and showing that the only way to have a linear relation among the vectors is for the coefficients to be 0. That's our usual way of showing linear independence. Okay. We can also show that this set of vectors spans R2 because no matter what vector in R2, this is an arbitrary vector in R2 that has components x and y, I can find constants C1 and C2 so that the linear combination of these two vectors gives me the vector in question. He's just showing algebraically here what I showed geometrically up here. Okay, so these two things are important to show in order to show that a set of vectors is a basis. Here's another example in the vector space of linear polynomials. Okay, linear polynomial means polynomial of degree 1. So we have a constant term and an x term. Here's one possible basis. This is a linear polynomial, 1 plus x. Here's another linear polynomial, 1 minus x. We can check that this is a basis the very same way. First, we verify that it's linearly independent. In other words, form a linear combination and show that that implies that the coefficients must be 0. And the second thing you have to show is that, in fact, these two polynomials do span the space of linear polynomials. So write an arbitrary linear polynomial as a linear combination of the two polynomials in the basis. You can solve for C1 and C2, and that shows that I can always express any linear polynomial as a linear combination. The span of these two vectors is the set of linear polynomials. Okay. All right, here's a basis for M22. Okay. Now, you can kind of see that. Certainly these are linearly independent. There's no way to take a constant C1 times this plus C2 times this plus C3 times this plus C4 times that and get 0. In fact, this set of matrices M22, it can really be identified as R4. You're just writing R4 in a different shape. And you can show in the same way that this is a basis for this vector space. And here's another basis. This one is a little bit more difficult to show, but in fact it is a basis, and you can use the very same techniques to show this. Well, here's a basis for R3. Notice the simple form, 1, 0, 0, 0, 1, 0, 0, 0, 1. Those are just my 3 axes vectors. This is my x-axis, this is my y-axis, and this is my z-axis. These are just the unit vectors along these 3 axes. That's the unit vector here. This is the unit vector here. This is the unit vector here. Calculus books sometimes call these I, j, and k. I wrote x hat, y hat, z hat, but that's the same thing as I, j, and k. Okay, so you are familiar with bases from, okay. All right, and you can generalize this notion of basis. This is for a 3-dimensional space. For n-dimensional space, you can take the set of vectors. The first vector has a 1 in the first component. Second vector has a 1 in the second component. The last vector has a 1 in the last component, and so on. Okay. Notice actually that if you wrote this sequence of vectors as a matrix, this would be the identity matrix. And that's going to come in. It's going to be important later. Just wanted to show you that. Same here. This is the 3 by 3 identity matrix. This is the n by n identity matrix. Okay, and you can use the same methods to show that these are both bases. This is called a standard or natural basis. Okay. All right. Although a basis is defined as a sequence, it's common practice to be sloppy and call it a set. So usually we don't distinguish between 2 bases that are in different orders. So I may fall into that, slip into that. Just be forewarned that you can, for most common purposes, you can think of basis as a set. The order in which the vectors are presented is not extremely important. Okay, so here's our first theorem. In any vector space, a subset is a basis if and only if each vector in the space can be expressed as a linear combination of elements of the subset in one and only one way. All right, before we move on to the proof, let's go and look back at our definition of basis to remind ourselves. A basis for a vector space is a sequence of vectors that's linearly independent and spans the space. All right, so going back to this theorem, is a spanning set that's linearly independent. So let's compare that to what this says. Here, this basis, if each vector in the space can be expressed as a linear combination, okay, now that's exactly the same thing as saying spanning set. These two are equivalent. The basis is a spanning set is the same thing as saying every vector in the space can be expressed as a linear combination. Okay. So the two things that we need to show equivalent are linear independence and uniqueness. That there's only one way to express every vector in the space as a linear combination. So basis gives me a unique representation of every vector. Okay, I could write that, say, as C1, X1. Let's take an arbitrary vector V. I can write V as C1, X1 plus Cn, Xn. And these coefficients C are unique. There's only one way to express this arbitrary vector in the space as a linear combination of basis vectors. All right, so let's go to the proof and see what's going on. All right, so here we have the sequence is a basis if and only its vectors form a set that spans and it's linearly independent. A subset's a spanning set if and only if each vector in the space is a linear combination of elements in at least one way. Okay? Thus, we need only show the spinning subset is linearly independent if and only if every vector in the space is a linear combination of elements from the subset in at most one way. Okay? Spanning set means at least one way. If I can get linear independence is equivalent to at most one way, then I have the equivalence of these two notions. All right, so let's consider two different expressions of a vector as linear combinations of the members of the subset. So let's rearrange the two sums and if necessary add some 0.bi terms so the two sums combine the b's in the same order. Okay, so here we have two different expressions for v in the vector space in terms of this basis b. Okay. Now we can set these two equal because v equals v. We can do some algebra and come up with this linear relationship among the b's. But we know that these b's form a basis. Okay? So the only way for this to happen is if C1 equals D1 all the way up to Cn equals Dn. Okay, so asserting that each coefficient here is 0, asserting that this is 0, this is 0, this is 0, is the same thing as asserting that Ci equals Di for each I. In other words, these two different expressions are really actually the same expression. That means that V can be expressed as a linear combination and at most one way. And what made that possible, the thing that made that possible was the fact that there is no linear relation relating the B's because they're linearly independent. Okay? So the upshot is, if we have a basis, we have a unique representation of every vector in the vector space. Okay, so we use that to make a definition. In a vector space with basis B, the representation of V with respect to the basis B is the column vector of the coefficients used to express V as a linear combination of the basis vectors. Okay, so here it is. This is the representation of V with respect to B. It's this coefficient. And these coefficients satisfy that the vector V is the following linear combination of basis vectors. And these are called the coordinates of V with respect to B. Now this accords with our usual notion of coordinates. For instance, if I have the standard basis, ijk, and I have a point here, maybe it's 3, 4, 5. I call it this, or put a vector here like that. What is that? That's 3i plus 4j plus 5k. So you can see that the coordinates 3, 4, 5 are exactly the coefficients of this vector with respect to the standard basis. So this idea of coordinates is the same idea that we're used to. Here's another example. We saw that in the polynomials of degree 1, one basis is 1 plus x, 1 minus x. As part of that, we computed the coefficients needed to express a member of P1 as a combination of basis vectors. Okay, we showed that if this linear polynomial is a combination of these two linear polynomials, then the coefficients are related in this way. Okay, so for instance, here's one example. Using this formula, we can show that 3 plus 4x is this linear combination of 1 plus x, 1 minus x. Here are the coefficients, 7/2 and minus 1/2. So that's my representation of 3 plus 4x in terms of the basis 1 plus x, 1 minus x. Okay. So with respect to R3's standard basis, E3, the vector V, 2 minus 3, 1/2, has this vector, 2 minus 3, 1/2. So this is like the example that I just showed. Here we have ijk. The x coordinate is 2, the y coordinate is minus 3, and the z coordinate is 1/2, so it'd be somewhere out here. That wasn't good. Let's be somewhere out here. And this vector here can be thought of as the, well, my picture is not so good, but similar to the picture I drew already, that this vector can be thought of as 2i minus 3j plus 1/2 k, and then identifies with the point 2 minus 3 1/2. Okay. All right, we'll stop here and go on to dimension in the next video.